Hello everyone. My name is Justin Vaughn, and I'm from Basis Parkland Harbor International School. Today, I'm gonna introduce a very important concept to you guys, which is social network analysis. First, let's start with the introduction. So, what is network analysis? Social network analysis is a method by which one can analyze the connections across individuals or groups or institutions. That is, it allows us to examine how political actors and or institutions are interrelated. So the advantage of social network analysis is that unlike many other methods, it focuses on interactions rather than on individual behavior. Network analysis allows us to examine how the configurations of networks influences how individuals and groups, organization, or system function. And it also can be applied across disciplines. There are social networks, political networks, electrical networks, transportation networks, and so on. So these are some important concepts that I'll briefly introduce it to you guys. Before we discuss the strength of weak ties and small worlds, let's just go over some basic concepts. A node or vertex is an individual unit in the graph or system. If it is a network or legislators, then each node represents a legislator. A graph or system or network is a set of units that may be, but not necessarily connected to each other. An edge is a connection or tie between two nodes. A neighborhood N for vertex or node is the set of its immediately connected nodes. Degree. The degree K of a vertex or node is the number or other nodes in its neighborhood. In an undirected graph or network, the edges are reciprocal. So if A is connected to B, B is a definition connected to A. In a directed graph of network, the edges are not necessarily reciprocal. A may be connected to B, but B might not be connected to A. Think of a graph with arrow indicating directions of the edges. Okay, now let's discuss the meaning of strength of weak ties. The strength of weak ties. A person called Granovetters has invented this theory and considered one of the most important psychology papers written in the recent decades. Argued that weak ties could actually be more advantageous in politics or in seeking employment than strong ties, because weak ties allow an individual to reach a higher number of other individuals. This person observed that presence of weak ties often reduce path length, which is distance, between any two individuals, which led to the quicker diffusion or information. So now is small world. So consider the related concept of small world, another concept that has emerged in network analysis. But for some background, let's discuss some different possible types of graphs, plus the concept of cluster, clustering and diameter. Two possible graphs, almost at opposite ends of spectrum, are random graphs and regular graphs. A small world can be thought of in between a random and a regular graph. So let's first start with the background of random graphs. In a random graph, each pair of verticals ij has a connecting edge with an independent probability of p. This graph, let's say, for example, if you count this graph, it has 60 nodes, and when you think about the connections, there are so many, and according to the internet, there are like 120 possible connections and 19 actual connections, and so that's about 1/7 probability that any two nodes will be connected to each other. In a random graph, the presence of a connection between A and B as well as connection between B and C will not influence the probability of a connection between A and C. So this is a regular graph, which is different from the random graph before. A regular graph is a network where each node has the same number of neighbors, that is, each node or vertex has degree k. A k-degree graph is seen at the left. Let's say k equal to 3 because each node is connected to 3 other nodes. That is, there are 3 nodes in each node's neighborhood. So this is clustering coefficients. Clustering coefficients were introduced by a person, which is a very pretty hard to pronouncing name. So as a way to measure how close a node or vertex that its neighbors end from being click or a complete graph within a larger graph of networks. The clustering coefficient of a node is the number of actual connection across the neighborhoods of a particular node as a percentage of possible connection. The clustering coefficient for the entire system is the average of clustering coefficient for each node. The formula is pretty confusing, I'm still thinking about understanding this. But let me just introduce it to you guys. The formula, which is on the right, is the total number of possible connections for an undirected matrix. Think in terms of a matrix, the total number of possible connections is half of the total of cells after subtracting the diagonal. So here's an example. For legislators, whether they serve on at least one committee together, this is an undirected matrix. If legislator A serves with legislator B on a committee, then legislator B serves with legislator A on a committee. So the possible number of connection in this matrix is 6, and k equals to 4 legislator, and then we just plug in the formula, then we got 6. The clustering coefficient for legislator A is 2/3, and which is connecting to 2 out of a possible 3 other legislators. This is the same is true of legislator B. Legislator C and D each have a clustering coefficient of 1/3. The average of those 4 clustering coefficient is 5, and note that across the entire network, 3 of 6 of all possible connections are actually made. This is the formula of clustering coefficient for the system. N equal to number of nodes, C equals to clustering coefficient for each node. And note that the clustering coefficient for undirected graphs is a bit different than the clustering coefficient for directed graphs. There are twice as many possible ties. A non-reciprocated edge counts for 1 tie, and a reciprocated edge counts for 2 ties. So in an undirected graph, if a node is connected to 4 other nodes, and among those 4, only the first and the third are connected, the clustering coefficient is 1/6, one actual connection out of 6 possible connections. Clustering refers to how connected your neighbors and to each other, relative to how connected they could be. Now let's talk about network diameter. So first, let's just talk about graph diameter. The graph diameter is the longest shortest path between any 2 vertices or nodes. The graphs above have diameter of 3, 4, and 7 respectively. The graph on the right has a relatively large diameter because it makes at almost 7 edges to travel between one node to another. The 2 nodes at very bottom of the network are not very closely connected. Let's just skip this, it's not very important. Here's some research. The importance of networks can also be seen in much social capital research. Social capital research often examines the connections across individuals and the consequences of the number and types of those connections for groups, organizations, and for individuals. For a review of this research, I will just skip this research. And these are how the network analysis applies to the political science, which is not very important. So my class will stop here. Thanks for listening, and goodbye.